Right, and so you might be thinking at this point, why does this velocity, why does it, if we're holding our height, so we understand why going deeper increases the pressure, but let's assume that we hold our heights the same. Why does an increase in velocity mean that we necessarily are going to have a lower pressure? And so for this, we usually look at what we call a Venturi-meter, and it looks something like this.
While he draws that, I'm just writing a side note I just thought of to the side, but you can just read it. So I just want to let you know, don't feel interrupted. I'm just writing something.
And so as we've established from continuity, this fluid going through a smaller cross-section necessarily must speed up. And then the question becomes, where does that force that's speeding it up, because, our equation is F equals ma still applies. And so where is this force coming from to speed this up? Well, it really comes from a pressure gradient, or a difference in pressure. Let's assume that we have, a nice little block of water. And in order for this to speed up, to be consistent with continuity, it has to accelerate this way, meaning that there has to be more pressure on this side than on this side. And that, of course, is a net force that accelerates it that way. And so, because it has higher velocity, it has lower pressure, it's conserved the same amount of energy and just changed it from one form to another. Now, a sort of interesting thing that follows from this concept that all else being the same, liquids at a higher velocity will have a lower pressure, is the airplane wing. And so we have this, air that comes through the airplane wing. And what ends up happening is that the surface, the distance that the fluid, again, air is a fluid, must cover is longer along the top surface of the wing. And so in order to do that, the air has to go a little bit faster. So the air going faster at the top of the wing means that air has a lower pressure. And so you have a slightly lower than atmospheric pressure acting on the top of the wing, and normal atmospheric pressure acting on the bottom, and that creates lift. So you're actually going to have a net effect pulling the airplane up. You can think of this as just a normal pressure, and this is essentially a lack of pressure, as if the thing is actually being sucked up by a vacuum. That's one way to look at it. In reality, it's just there's a higher pressure at the bottom. Either way you look at it, this is the main principle behind how airplanes fly.